We can learn a lot by looking at different solutions to the same problem and then comparing and contrasting those solutions. That's exactly what we're going to do today. We're going to evaluate this nice integral over here two different ways. And, well, we'll sort of see what we get using both methods, and you'll see that the solution immediately looks a little bit different, but we can reconcile that, and we'll get to that at the end. Okay, so anyway, let's see what we have. We have the integral from 0 to pi over 2 of dx over y squared minus 2y cosine x plus 1. So observe that we have this parameter y in the mix, but at the heart of it, this is an integral with respect to x. So our first method will be to start with Euler's formula for the complex exponential and then go from there. So that says that e to the ix is cosine x plus I sine x. But after a little bit of manipulation, you can see that 2 times cosine x is e to the ix plus e to the minus ix. So that's going to be our first step, is to replace 2 times cosine x with this sum of these two, well, imaginary exponentials. Okay, so we'll have dx over, now we'll have y squared, and then minus y times e to the ix plus e to the minus ix, and then plus 1. Where I brought this 2 to multiply into the cosine, just to use this, in its simplest form. But now let's observe that e to the ix times e to the minus ix is 1. So this motivates us a really nice factorization of the denominator. So here we have the integral from 0 to pi over 2, and then we'll have dx over, so this is going to be y minus e to the ix times y minus e to the minus ix. And you can see if you multiply this out, well, you'll get exactly what we had before. So our next step is to do a partial fraction decomposition. Actually, in order to do this, I'm going to introduce a little bit of maybe a variable just for the purposes of this partial fraction decomposition. And I'll set it equal to u, and it'll be e to the ix. But that means e to the minus ix is equal to 1 over u. Okay, good. But then what do we have? Well, we're going to have 1 over y minus u times y minus 1 over u is equal to, well, we want to decompose that. But before we decompose that, I really want this to be a polynomial in the denominator in our variable u. So I can write that as, well, by multiplying the numerator and the denominator by u, I'll have u over, we'll have y minus u times uy minus 1. So keep in mind our variable of integration is x, so we really want to decompose this all in terms of thinking about x as the underlying variable, but since we did a change of variables, our u is our underlying variable. So that means we're going to take this object right here and set it equal to a over u minus y plus b over uy minus 1. Great, and then let's maybe just go ahead and bring this down so we all have it on the same line. Okay, great. So just to reiterate what's going on here, I'll box this in red. This is the boxed equation that we're using to do our partial fraction decomposition. Okay, so now from here, I'll multiply the numerator and the denominator by, well, the denominator that's existing on the left-hand side to clear everything out. And that's going to give me u equals a times uy minus 1 plus b times y minus u. Okay, nice. Now what we'd like to do is take out the u terms from both sides of this equation and the constant terms from both sides of this equation. So let's start with the u terms, and then I'll denote the constant terms just by this number 1. So the u terms, well, on the right-hand side, we'll have a times y plus let's see, the coefficient of u is minus b. So we'll have that is equal to 1. And then for the constant term, which like I said, I'll denote by just 1, what will we have? Well, we'll have b times y minus a is equal to 0. But now let's observe that we can take this b times y minus a equals 0 and say that a is equal to b times y. And then sort of pretty clearly we can take that and put it into our first equation, and that'll give us by squared minus b is equal to 1, which tells us that b is equal to 1 over y squared minus 1, just by solving that pretty easily. But then a is equal to b times y, so that tells us that a is equal to y over y squared minus 1. Okay, but now we can put that right up here and then push it back into our integral. So now we'll have the integral from 0 to pi over 2 of, so we'll have a over y minus u. So observe that that will be, let's see, y over y squared minus 1 over y minus e to the ix. And then we'll have plus b over uy minus 1. So that'll be plus 1 over y squared minus 1 over, like I said, y times u, which is e to the ix times y minus 1 dx. Okay, so now that we're done with that calculation, we'll get rid of it and then we'll work on this term. Okay, so now we'll see that these things are pretty close to geometric series. So let's get them until they're exactly like, well, summed up geometric series so that we can re-expand them. So I'm going to factor out a 1 over y squared minus 1 along with a minus 1 because I want to flip the order of subtraction in both of these terms. So that'll be 1 over 1 minus y squared. And then I'll have my integral from 0 to pi halves of, now I'm also going to multiply the numerator and the denominator here by e to the minus ix. So that's going to leave me with the y times e to the minus ix over 1 minus y times e to the minus ix. Because remember, I switched the order of subtraction because I brought that minus sign out. And then, well, this thing is pretty much good to go. I'm just going to switch the order of subtraction. So that'll be plus 1 over 1 minus y times e to the ix dx. Great. And now I can, well, expand each of those as geometric series. So that's going to leave me with 1 over 1 minus y squared. And then we'll have our integral from 0 to pi halves of y times e to the minus ix times the sum as n goes from 0 up to infinity of y to the n e to the minus inx. So that's our first term. So let's color code this. So this term right here has been expanded into this infinite sum. And then likewise, we'll expand this second term as well. And that'll expand as the sum as n goes from 0 up to infinity of y to the n e to the inx. Okay, great. Now let's see, we have this dx. Okay, but now let's look carefully at this second term and observe that we can bring the number 1 out. So the number 1 is the first term, and then we'll have plus, let's see, the sum as n goes from 1 up to infinity of y to the n e to the inx. Great. And then likewise, we can take this first term and we can multiply this y times e to the minus ix inside and then re-index to get the sum as n goes from 1 to infinity of y to the n e to the minus inx, where I just did a bit of re-indexing there. Then, well, I've got this free 1 out here and I can smash those two sums together. So that leaves me with 1 over 1 minus y squared. I have my integral from 0 to pi halves. And then I'll have 1 plus the sum as n goes from 0 to infinity of y to the n, I have e to the I n x plus e to the minus I n x. Oh, and this sum should have started at 1 now because of all that stuff that I just did. Okay, so there I am. But now we can apply this rule one more time, kind of in the reverse direction that we did before, to rewrite this as 2 times cosine of nx. Okay, so let's see where we are. We have 1 over 1 minus y squared, and then we can integrate out this number 1 term. The length of the interval is pi over 2, so we can get a pi halves there. And then we'll change the order of summation and integration. So that'll give me the sum as n goes from 1 to infinity of y to the n. And then we'll have our integral from 0 to pi halves of cos nx dx. Great, so there's where we are so far. Now we will take this integral term here and see if we can do any simplification to it. And in fact, we can. So let's see that that's going to turn into 1 over n times sine of nx, where I evaluate that from 0 to pi halves. But that's pretty clearly going to give me 1 over n times sine of n pi over 2. Okay, but now notice that that's going to give us 0 when n is even, because sine of an integral power of pi is even. And then that's going to give me plus minus 1 when n is odd. And in fact, it's simply going to alternate between being positive and negative 1. So let's observe for n equals 1, we'll get a positive 1. For n equals 3, we'll get a negative 1. For n equals 5, we'll get a positive 1, and so on and so forth. So that allows us to rewrite this sum that we have as the sum as n goes from 0 to infinity of minus 1 to the n times y to the 2n plus 1 over 2n plus 1, where I replaced n with 2n plus 1. And notice this has exactly the same effect. When n is equal to 0, the denominator is 1, and we get something that's positive. When n is 1, the denominator is 3, and we get something that's negative. When n is 5, well, it matches exactly what we want as well. Okay, so let's maybe start the next board with this line right here where we have replaced our sum, as we did above. So this is where we ended up on the last board. I'd like to point out that for the last step, or maybe step and a half or 2 steps, I forgot to write this 2, but I've replaced it right here. So that didn't affect any of our calculations. Okay, so now let's work on this sum that we have, because if we can determine a nice closed form for this yellow underlined sum, then we're good to go, and we have like a really nice solution. So let's see. It looks like an integral has occurred, and I say that it looks like an integral has occurred because we have the same exponent in the numerator that we have as a denominator. So in fact, what's going on here, or what looks like is going on here, is we've got the sum as n goes from 0 to infinity of minus 1 to the n. And then I'm going to write this as t to the 2n plus 1 over 2n plus 1, where I've evaluated that from 0 to y. So I like to write it like that because it looks like I have a 0th integral here, which is just really evaluation at endpoints. And I can change a 0th integral to a first integral with the fundamental theorem of calculus. And that's by taking a derivative and replacing this as an integral. So that'll leave me with the sum as n goes from 0 to infinity of minus 1 to the n, and then the integral from 0 to y of t to the 2n dt. So, well, that's what I get if I take that derivative. Now let's replace the order of summation and integration. So that leaves me with the integral from 0 to y of the sum as n goes from 0 up to infinity of minus t squared raised to the n power dt. So I wrote it like that because now this object right here looks like a geometric series where my common ratio is minus t squared. So that's going to leave me the integral from 0 to y of 1 minus negative t squared, or 1 plus t squared dt. But that's clearly equal to the inverse tangent, the arctan of y. So now we can put that back into our, expression that we have right here. And we have 1 over 1 minus y squared pi halves plus 2 times the arctan of y. And that's the end of our first pass through this integral. Okay, so now let's move on to the second take. For our second journey through this integral, we're going to use the so-called Weierstrass substitution. In other words, the half-angle tangent substitution. So we'll set t equal to the tangent of x over 2, and then via a pretty simple calculation, we can get that dx is 2 dt over t squared plus 1, and cosine of x is 1 minus t squared over 1 plus t squared. And those are all of the parts that we really need here for our calculation. Obviously, there's also going to be an expression for sine of x, but we don't need that. So here we'll have the integral of, so we'll have 2 dt over, we have y squared minus 2 times y times 1 minus t squared over 1 plus t squared plus 1, and then this whole denominator is multiplied by t squared plus 1. Then we should talk about how the bounds of integration change. So when x is equal to 0, tangent of 0 is 0, so t is equal to 0. When x is equal to pi over 2, we have tangent of pi over 4, which is 1. So that changes from 0 to 1. So that's pretty nice. But now let's multiply out this denominator, and we'll see that we have the integral from 0 to 1 of 2 dt over, so now we'll have y squared times t squared plus 1 minus 2y times 1 minus t squared plus t squared plus 1. But our integral is with respect to t, so we really need to collect all of the t terms in the denominator. So I'm going to bring this 2 out, and then we'll have the integral from 0 to 1. We have dt, and let's see what our t squared term is. So it's going to be y squared plus 2y, because the sign will change, and then plus 1 from this here right here. So here we have, like I said, y squared plus 2y plus 1 t squared. And then notice we don't have any linear terms in t, we only have constant terms. And those constant terms are y squared minus 2y plus 1. So let's write that, y squared minus 2y plus 1. But observe that those are both perfect squares. So, and by those, I mean this blue underline right here, the coefficient of t squared, and then this magenta underline right here, the constant term. So let's factor those out. That'll leave me with 2, the integral from 0 to 1 of dt over, I'll write that as 1 plus y quantity squared times t squared plus 1 minus y all squared. But that has a fairly standard formula for its integral, so we'll just jump right to that. We have 2 over 1 minus y squared. We get that from 1 plus y times 1 minus y. And then we'll have the inverse tan, so the arctan of 1 plus y over 1 minus y times t. We need to evaluate that from 0 to 1. Okay, nice. But now let's observe that that's equal to 2 over 1 minus y squared times the arctan of 1 plus y over 1 minus y. But that looks a little bit different than our original answer, so let's maybe consolidate these down so that we make sure they are the same. And in order to do that, we need a certain tangent or arctangent formula. And that's the arctan of A plus the arctan of B is equal to the arctan of a plus b over 1 minus ab. So now we can use that where a is equal to 1 and b is equal to y, or kind of vice versa. And that's going to leave us with 2 times, or 2 over 1 minus y squared. And then we'll have arctan of 1, which is pi over 4. And then we'll have plus arctan of y. But now multiplying the 2 through, we'll change that pi over 4 to a pi over 2, and then we'll have 2 times the arctan of y. We'll have exactly what we have over here. Okay, so there you have it. We just evaluated this integral 2 different ways, and that's a good place to stop.